Space. The Perseid meteor shower is with us again, which, like other meteor streams during the year, is associated with a comet, in this instance Swift-Tuttle. In today's programme, our main theme is comet ISON, which is expected to be a brilliant sight in the sky this winter, and comets in general. But first, let us take a look at the highlights of the August night sky. In August, the nights are beginning to get longer as we move closer to the autumn equinox. Sunset on August the 1st is 9:06 p.m. and 8:16 p.m. at the end of the month, the average sunrise time being 6:35 a.m. After 9:30 p.m, look into the northeastern sky, where you will see the W-shaped constellation of Cassiopeia, and below this is Perseus the hero. Both contain bright stars and are quite easy to find. Midway between these constellations is the radiant of the Perseid meteor shower. The maximum occurs on the night of August 11th and 12th when the moon is out of the way, and you should be able to count over 70 shooting stars an hour. The Perseid radiant is associated with the comet Swift-Tuttle, which was discovered in 1862 and orbits the Sun every 133 years. Every year at this time, the Earth passes through the debris trail of comet Swift-Tuttle, which results in the Perseids. The best time to see the greatest number of Perseid meteors is an hour or two before dawn. However, you can still see Perseid meteors any time during the first half of August. There are a number of meteor showers on view during the year, which are also associated with comets of their own. For example, the Leonids, which reaches maximum on the night of the 17th of November, is associated with the comet Tempel-Tuttle. I'll have more to say about comets later in the programme. Now, what about the moon? New moon occurs on August the 6th, first quarter is on August the 14th, full moon occurs on August the 20th, followed by last quarter on August the 28th. As the moon crosses the night sky, as it orbits the Earth, it passes close to some bright stars and planets, making ideal photo opportunities. On August the 1st, the Hyades in Taurus will be 3 degrees south of the moon's present disk. When it's the turn of the planets. On August the 3rd, Jupiter will be 5 degrees north of the moon, followed by Mars on August the 4th. Venus is 5.8 degrees north of the moon on August the 10th, and finally Saturn will be 3.4 degrees north of the moon on August the 13th. Mercury, the inner planet, will be at superior conjunction with the Sun on August the 24th, and is therefore effectively out of view. Venus is visible low down in the western sky after sunset, shining at magnitude -3.9 on August the 1st, and its phase as seen through a telescope is becoming noticeably gibbous. That is to say, neither full but greater than half. The lovely ring planet Saturn is still quite prominent in the southwestern sky after sunset in the constellation of Virgo. It shines at magnitude +0.7 and is about 16 degrees above the horizon. Saturn is steadily drifting towards the more brilliant Venus in the west. There is still plenty of time to observe Saturn through a small telescope, which will show the rings nicely on view. At 10:27 p.m. on July the 19th, the Cassini spacecraft in orbit around the planet took a photograph looking back towards planet Earth from a distance of 898 million miles. Earth can clearly be seen as a small blue star-like point in the images. We cannot expect anything better than that. Mars is now on view in the east before dawn, shining at magnitude +0.6. Mars rises 2¼ hours before the Sun in the constellation Gemini the Twins. The more brilliant planet Jupiter is nearby. Mars shines with a distinctly sandy hue, and its angular diameter of 3.9 seconds of arc is not very great, so don't expect to see any more than the planet's tiny disk through a telescope. Telescopes of 6 inches for a refractor and 8 inches for a reflector are needed to begin to see any detail. Mars is the fourth planet out from the Sun, lying at a mean distance of 141.6 million miles and is about half the size of the Earth. The planet takes over 686.9 Earth days to orbit around the Sun once, which is slightly more than 1.88 of 8 years. The planet also has two small moons of its own, Phobos and Deimos, which in Greek mythology mean fear and terror. This is very fitting since Mars itself is named after the Roman god of war. Today we are learning considerably more about Mars from the landers and rover vehicles on its surface and spacecraft in orbit around the red planet. NASA's Spirit, Opportunity and Curiosity, the present rovers on Mars, are telling us that once there was a significant oxygen-rich atmosphere around the planet and Mars had a lot of water on its surface. It is now believed that at some point in its past, Mars was hit by a large meteorite which evaporated the planet's atmosphere into space, leaving behind what we have today. Finally, the giant planet Jupiter is visible to the upper right of Mars, shining more brilliantly at magnitude -1.9 and gradually brightening during the month. Jupiter also lies in Gemini, rising more than 2.5 hours before the Sun. A pair of binoculars will show the planet's 4 bright moons, Io, Europa, Ganymede and Callisto, as they move around Jupiter's disk, while a small telescope will show the horizontal cloud belt. In a 3-inch refractor telescope, you may even catch a glimpse of the planet's famous Great Red Spot. As seen in the telescope, Jupiter has an angular diameter of 32.9 seconds of arc, which is more than 10 times that of Mars. Before we move on, some news about the Earth's Van Allen radiation belt. Prior to the space age, the possibility of trapped charged particles had been investigated by Christian Birkeland, Carl Stromier and Nicholas Christopoulos. The existence of the belts was confirmed by satellites Explorer 1 and Explorer 3 missions in the early 1958 under Dr. James Van Allen at the University of Iowa. The trapped radiation was first mapped out by Explorer 4, Pioneer 3 and Luna 1 in the 1950s. Based at the Johns Hopkins University, here is Applied Physics Laboratory project scientist Nikki Fox to tell us more.
Every single day we're seeing new and exciting data coming in. We're learning much more about the dynamics and the evolution of the radiation belts, why they're changing, how they're changing. We've seen them almost disappear completely. We've seen new belts that we didn't even know exist appear. Traditionally, we've always thought of an inner and an outer belt. What we've found now is that the outer belt has much more structure in it, and there is a storage ring, a separate ring, almost a permanent third belt that's there that we think is actually the home to the particles that are filling the outer belt.
This 2-year mission didn't quite get off the ground as originally expected. It was first delayed for 24 hours for a technical issue, and then it was followed up by some bad weather, which eventually led to another delay.
Then Hurricane Isaac rolled in to the Cape. That really put us back almost a full week. We actually had to roll the rocket back into the integration facility and shut the doors and protect it. But a few days later, we were back out again, ready to go, and it was worth every second of the stress of waiting for it. We launched at the end of August, and it was almost like the sun knew we'd launched and immediately switched on. We hadn't seen really any space weather events for really quite a long period of time, and yet within the first couple of days of the mission being up there, the sun threw a beautiful event our way. We were able to see a lot of very, very interesting science that we wouldn't have seen if we hadn't had this large event, and we certainly would never have seen it without the tremendous instrumentation on the 2 spacecraft. We've always known that there are waves and magnetic and electric fluctuations that go on in these belts, but with the more traditional 1 spacecraft, we could just see the wave and it would disappear. Now with the 2 spacecraft and also the most sophisticated instruments that we've flown in the belts, we're actually able to look at how these waves evolve, how they change, and how long they last. These waves are very important because they actually carry the particles that are in the belts. It's almost like the particles surf on these waves.
Now on to our main theme. Comet C 2012 ISON and the Realm of Comets moving around our solar system. From December the 2nd onwards, a clear sky is permitting. If you look into the eastern sky at dawn, you will be able to see the bright tail of Comet ISON pointing up from the horizon, and during the month the comet will slowly drift across the northern sky. The brightness of a comet is slightly difficult to predict. However, at the moment, it looks like reaching magnitude -4.9 on November 28th, when ISON is at its closest point to the Sun, perihelion, before fading to +5.6 at the end of December. Comet ISON will remain visible in binoculars until February 2014, when it will shine at magnitude +9. The last bright comet to be visible in the northern hemisphere was Hale-Bopp of May 1996, which reached magnitude -1.6, so Comet ISON should be a fine spectacle this winter. To put this into perspective, the Sun shines at magnitude -26, the full moon -12.5, and the planet Venus can reach magnitude -4.4. At the present time, the planet Mars in Gemini is shining at magnitude +1.8. Comet ISON will come to perihelion on the 28th of November 2013 at a distance of 1,100,000 miles from the centre point of the Sun. Accounting for the solar radius, ISON will pass 680,000 miles above the Sun's surface. Its trajectory is nearly parabolic, which suggests that it may be a new comet coming freshly from the Oort cloud. On its closest approach, ISON will pass about 6,730,000 miles from Mars on the 1st of October, and it will pass about 40 million miles from the Earth on the 26th of December. Comet ISON is a sun-grazing comet discovered on the 21st of September 2012 by Russian astronomers Vitaly Novitsky and Artem Novichonok. The discovery was made using the 16-inch reflector of the International Scientific Optical Network in Russia and the automated asteroid recovery program Kolitech. Pre-recovery images by the Mount Lemmon survey from January 2012 were quickly located. Observations by Swift suggest that the ISON's nucleus is around 5 kilometers in diameter, about 3 miles. A comet is not a massive solid body of the same type as a planet. It is composed of chunks of rock and ices surrounded by a vast envelope of tenuous gas. The tail is made up of even smaller particles and even thinner gas. One peculiarity is that the tail always points more or less away from the Sun, so that during its outward journey the comet moves tail first. It was formerly thought that this must be due to the pressure of sunlight. However, the true explanation is more complex. It involves a so-called solar wind, streams of particles moving outwards from the Sun in all directions, together with magnetic effects. We know what a comet looks like and what we are made of because 10 space probes have visited, measured and imaged comets since 1986. 5 went to Halle's comet, Giotto, Vega 1, Vega 2, Seiki-Geico and Suzy. 2 went to Comet Temple, Deep Impact in 2006 with a flyby and had an impactor probe, and Stardust next, followed in 2011. Comet Borrelli was visited by Deep Space 1 in 2001. Stardust went to Comet Wild 2 in 2006 and returned samples awaiting Earth scientists, and the Giotto probe survived its Halle's comet encounter in 1986 and then went on to visit a second comet, Greg Skillerep, in 1992. Comets are of 2 main types, known broadly as periodical and non-periodical. A periodical comet moves around the Sun in an elliptical orbit, returning to its perihelion, or closest point of approach, every few years. The comet with the shortest well-established period is Encke's of 3.3 years, while at the other end of the scale, Comet Herschel-Rigolot, last seen in 1939, has a period of 156 years. Since the comet shines mainly by reflected sunlight, even though it is excited to feeble luminosity on its own account when near perihelion, it can be seen only when reasonably close to the Sun and the Earth. However, the orbits of periodical comets can be worked out, and a large number can be predicted with confidence. Yet these periodical comets are by no means startling. Apart from Halley's, they are too faint to be seen without a telescope, and many never develop tails, so they look like nothing more than dim, rather hazy patches against the starry background. Since the comet shines mainly by reflected sunlight, even though it is excited to feeble luminosity on its own account when near perihelion, it can be seen only when reasonably close to the Sun and the Earth. However, the orbits of periodical comets can be worked out, and a large number can be predicted with confidence. Some of them are of great interest. For example, there is a comet known as Swift-Tuttle 2, whose orbit is much more circular than those of most other periodical comets, keeping it entirely between the orbits of Jupiter and Saturn, with the result that it may be seen each year, though powerful telescopes are needed to show it. But only Halley's comet is bright enough to arouse popular interest. Halley's comet has a period of 76 years. It has been observed regularly for more than 2,000 years now, though it was only in 1682 that Edmund Halley, the second Astronomer Royal, realised that it was a periodical, since he identified the 1682 comet with those of 1607 and 1531, and predicted that it would return once more in 1758, a forecast that was duly fulfilled, though Halley himself did not live to see it. The comet made its last appearance in 1986. At the moment we cannot see it, even though its position can be worked out accurately. It is still moving out in the far reaches of the solar system, beyond the orbit of Neptune, 3,206 million miles from the Sun, and it lies in the constellation of Hydra. It is not likely to be recovered until a year or two before its next perihelion passage in 2064. At its best, it has a considerable tail and is decidedly conspicuous from Britain, although it was rather disappointing in 1986. The really brilliant comets, which have been seen at intervals of much longer periods, amounting to hundreds, thousands or even millions of years. This means that they cannot be predicted, and so far as we are concerned, they make only one perihelion passage. Donati's comet, seen in 1858, is a typical case. Its period cannot be less than 10,000 years, and it is probably more, so that we are entitled to class it as a non-periodical, even though it is a true member of the solar system. Great comets were reasonably frequent during the last 2 centuries. Particularly notable was the comet of 1811, whose tail is said to have stretched for a long way across the sky. In this case, the tail was more or less straight. By contrast, the 1744 comet, which was of comparable brightness, has 6 separate tails, all curved. Another spectacular comet was that of 1843, whose head was larger than the Sun, even though its total mass was extremely small by planetary standards. Of the rest, the great comet of 1882 should be mentioned here, because it was what is known generally as a sun grazer, of the same kind as comet ISON of this winter. It passed perihelion only a few hundreds of thousands of miles above the bright surface of the Sun, so that it was intensely heated. In January 1910, another great comet made its appearance. It was bright enough to be seen with the naked eye in broad daylight, at least from the southern Europe and countries in lower latitudes, and it is therefore known as a daylight comet. It too had a long tail, and it was much brighter than Halley's comet, which returned to perihelion later in the year. Various short period comets have been known to disintegrate. A famous case being that of Biela's comet, which was last seen in 1852 after it had split into 2 separate parts, and which has never been observed again, even though its debris has manifested itself as a meteor shower. The Andromedates, which reached maximum activity on the night of November the 9th. On the morning of the 21st of October 1852, the comet was expected to be very close to the Sun and also close to the star Spica in Virgo. Astronomers all over the world were on watch, and yet Bailey's comet could not be found. The last bright comet to be seen in the northern hemisphere was Hale-Bopp. Hale-Bopp became visible to the naked eye in May 1996, and although its rate of brightening slowed considerably during the latter half of that year, scientists were still cautiously optimistic that it would become very bright. It was too closely aligned with the Sun to be observed during December 1996, but when it reappeared in January 1997, it was already bright enough to be seen by anyone who looked for it. As the comet approached the Sun, it continued to brighten, shining at second magnitude in February and showing a growing pair of tails. The blue gas tail pointing straight away from the Sun, and the yellowish dust tail curving away along its orbit. At its brightest, Hale-Bopp had a magnitude of -1.6. On March the 9th, there was a solar eclipse in China, Mongolia and eastern Siberia, which allowed observers there to see the comet in broad daylight. Hale-Bopp had its closest approach to the Earth on March the 22nd, 1997, at a distance of 122 million miles. As it passed perihelion on the 1st of April 1997, the comet developed into a spectacular sight. It shone brighter than any star in the sky except Sirius, and its dust tail stretched 40 to 45 degrees across the sky. The comet was visible well before the sky got fully dark each night, and while many great comets are very close to the Sun as they pass perihelion, Comet Hale-Bopp was visible all night to Northern Hemisphere observers. The last naked eye observations were reported in December 1997, which meant that the comet had remained visible without aid for 569 days, or about 18 and a half months. The previous record had been set by the Great Comet of 1811, which was visible to the naked eye for about 9 months. Our solar system is made up of the Sun in the centre, and as we move outwards, we come to the 4 rocky planets: Mercury, Venus, Earth and Mars. Then there is a zone of rocky debris called the asteroid belt. Over 3,000 of them are known. The 4 biggest asteroids are Ceres, Pallas, Juno and Vesta. Ceres is classed as a dwarf planet and has a diameter of 590 miles. Then comes the giant gaseous planets, Jupiter, Saturn, Uranus and Neptune. Comets are believed to have 2 separate points of origin in the solar system. Short period comets, those with orbits of up to 200 years, are generally accepted to have emerged from the Kuiper belt, or a scattered disk. 2 linked flat disks of icy debris beyond Neptune's orbit at 279 million miles, and generally extending out beyond 930 million miles from the Sun. The orbits within the Kuiper belt are relatively stable, so very few comets are believed to originate from there. The scattered disk, however, is dynamically active and is far more likely to be the place of origin for comets. Comets pass from the scattered disk into the realm of the outer planets, becoming what are known as centaurs. These centaurs are then sent further inward to become short-period comets. Long-period comets, such as Comet ISON and Hale-Bopp, whose orbits last for thousands of years, are thought to originate in the Oort cloud. The Oort cloud is thought to occupy a vast space from somewhere between 187 and 465 billion miles from the Sun, to as far as half a light year. Some estimates place the outer edge at between 1.6 and 3 light years. The region can be subdivided into a spherical outer and a donut-shaped inner Oort cloud. The outer cloud is only weakly bound to the Sun and supplies the long-period comets to inside the orbit of Neptune. The inner Oort cloud is also known as a Hills cloud, named after J.G. Hills, who proposed its existence in 1981. Models predict that the inner cloud should have tens or hundreds of times as many cometary nuclei as the outer halo. It is seen as a possible source of new comets to resupply the relatively tenuous outer cloud, as the latter's numbers are gradually depleted. The Hills cloud explains the continued existence of the Oort cloud for billions of years. To put simply, meteor showers like the Perseid are the debris left behind by comets along their orbital paths, which the Earth intersects at various times during the year. As these pieces enter the atmosphere, they burn up due to friction with the air, and they are then seen as shooting stars. Comet ISON looks like it will be a splendid sight during December, and may even become known as a Christmas comet. We'll just have to wait and see. And that's all we have time for this week. Thank you for watching. Until next time, goodbye for now.